This evening, please welcome Doug, W2VX. Now, Doug is going to be having 10 minutes to tell us about a project that you're working with, digital synthesis. And so...
direct digital synthesis.
Direct digital synthesis.
Say that 5 times real fast.
Can't do it.
Okay.
I'll let you.
Right.
Thank you.
Okay, thanks. So I have control of the slides with this job. Is this IR or RF? Oh, anyway.
Digital synthesis.
It's digital synthesis. I always love a bench project because I have a background in firmware design and digital electronics, and so whenever I'm reading QST, I try to skip over these bench projects because I always get engaged in them. And then I wonder why. But this one turned out to be a lot of fun, and so I just thought I'd fly over at about 100,000 feet. Let's see here. Okay, before I go into this, I want to do a little check on the audience. How many of you have heard of Arduinos? Show of hands. Okay, how many of you have programmed one? Okay, that's pretty good. There's also Espressive, system on a chip. People that have, good, we've got a few people, okay. Anybody familiar with direct digital synthesis VFOs? Got a couple of people, 3, all right, 4. Great. Anybody in here ever programmed an FPGA? Oh, I love this. Good, let's talk later. I love it. It doesn't really have anything to do with, with this project, but that way I can find out who to talk to. Familiar with test equipment? All of these or some of these? Okay. Specifically, probably spectrum analyzers. How many people have used a spectrum analyzer? Okay, good, perfect. All right. So this is the QST Magazine project. In there, there's an article about building a 6-meter radio out of components that you can buy off of eBay or Alibaba or wherever, and you glue them together, and voila, you end up with a nice 6-meter radio. I don't need another 6-meter radio, anything but. But there are a couple of components that were on this. This little jobby right here turns out to be, that's the actual chip. It's a direct digital synthesis frequency generator. This particular one should work in the range of a 6-meter band. And I have a background in digital work, and so I looked at it and said, well, it's got certain characteristics. I wonder how well it actually performs. So this is about how I figured that out. So in order to do this work, I thought, okay, we need an agile VFO. And an agile VFO means that it'll tune to a variety of frequencies, generally fairly a broad band of frequencies, and it'll hop from one frequency to the other almost instantaneously. These direct digital synthesis frequency generators are fairly low cost. The one that I bought was like 18 bucks on an evaluation board. They're relatively easy to implement because you wire it up to an Arduino or to an Espressive microcontroller. You send a few little pieces of information to it, and out the other side, out a couple of SMA ports, comes a sine wave of the frequency desired. I wanted to find out really how well do they perform, and what are the caveats. So there was also an interest of mine for experimenting with the output filters, because digital synthesis of sine waves generally creates a lot of harmonics. So this is sort of the layout of my test environment. There's a microcontroller that's hooked up to this direct digital synthesis board. Out of that comes a sine wave. Out of that, I feed it into an analog low-pass filter. And in the process, I have a logic analyzer that's looking at the digital interface between this microcontroller and the frequency generator. I've also got a spectrum analyzer that's taking a look at how close is the sine wave to actually producing the frequency that I want, and an oscilloscope to see how much jitter there is. And I do that before and after the filter, the low-pass filter. So that's what it looks like in a block diagram. What it really looks like is something like this on my bench. There's some test equipment, and then inside of this expensive test RF environment, those are the two devices that I've hooked together. I've also got a microphone hooked up to it so I can do a little bit of FM modulation. And 12-volt battery so that I don't get any harmonics out of my power source. This is just a little close-up, same thing as what you saw before. Construction of that takes maybe an hour. That's about 40 or 50.
Yeah, for you.
Yeah, for me. I do this a lot. So about 40 or 50 bucks worth of stuff. Okay, so I fired it up, and I'm taking a look at the spectrum analyzer, and I turned it on to, it says 50 megahertz up there. And before I just sat on 50 megahertz, I just let it sweep. And as you can see from this blue line, that's what the output looks like, and it's pretty ugly. One would expect, you know, just to have that right there. But of course, this is the digital domain, and we're trying to get into the analog domain, and so we've got a lot of harmonics. And one of the reasons that there are these many harmonics is because, well, we're pretty close to the Nyquist frequency on this, which means we're trying to push this particular chip a little bit further than it's really designed for, frequency-wise. So how do we get direct digital synthesis? The idea is we feed a number into this direct digital synthesis chip. Out of it comes this frequency. The frequency is actually constructed by discrete voltages that come out of a digital to analog converter. And this is showing a time series where, you know, somewhere along here and not necessarily in phase, we get certain voltages out. And everything looks like, where is the sine wave? Where is the sine wave? I had a hard time drawing a sine wave, so you'll have to forgive this sawtooth, but imagine that that's a sine wave, that red line, dotted line. And these blue boxes are basically the representations of the voltage that's coming out of the digital to analog converter. And there's all kinds of phase issues here. Things are not always lined up depending upon what frequency you pick. And that's why we have all those harmonics. And I thought, well, I just want 50 megahertz. So how do I just get 50 megahertz? And of course, anybody who's passed the radio exams knows, well, what you should do is put in some kind of an output filter. So I went to a website. I love websites. Put in a couple of parameters and boom, say I want an elliptic filter, third order elliptic filter. I picked one that was simple because they're easy to construct. It's 3 capacitors and an inductor. And when you actually build it, it looks like this. You know, say that's a penny. Well, these are the SMA connectors. I made the inductor by wrapping a piece of wire around the end of a pencil. Stuck a couple of, you know, approximately the right value small capacitors onto it. And when I ran the spectrum again, what I found was this harmonic is 12 dB down. Oh, what I did was I changed the frequency here. We're actually at 20 megahertz now because I wanted to get back into the spectrum, basically into the frequency that was better and more appropriate for this particular device. And what I found out was I still have a lot of harmonics, but I'm operating at 20 megahertz. I put the filter in. This is basically without the filter. And this is what it looks like with the filter in. So I've got almost 20 dB down. Almost all the harmonics are gone. And so these devices are actually pretty good when it comes to using them as a VFO, as long as you stay in a frequency range on the output, which is less than about 30 to 35% of the input frequency from the clock that's driving the chip.
So in this case, your low-pass filter was a 70 megahertz filter?
It turned out to be a 70 megahertz filter. I was trying to design it to be somewhere in the neighborhood of 55.
So your first harmonic there is in the 70.
This harmonic, this is actually 62.5 megahertz. Yeah. And it turns out that this is inside the filter, so it's passing. And because I pulled the frequency down to 20 megahertz, I'm not generating as much harmonic. And so the power in this first harmonic is much lower. Otherwise, it would be right up here. So there's two things going on there. Any other questions? I always love theory, but we're not going to go into that. That's where I start. That's actually my domain that I love. But I've discovered that theory only goes about 5% of the distance. And when I get to the bench, that's where the real learning occurs. This is just an example of some of the different kinds of chips that you can buy and their capabilities. Whatever you want, it's available. The manufacturers will build almost anything. The one that I'm going after next is the 809959, mostly because I can do frequency, phase, and amplitude key shifting with it all in one shot, and generates 4 frequencies and independent channels. That was sort of an introduction. If you want to know more, or if you know more, I'm in the back. I'd love to talk to you. All right?
What is the practical application that you're using this for yourself?
Mostly learning. I think that one of the practical applications that came up last month was you could use this as a sweep generator for a fairly low cost, low frequency spectrum analyzer. And you could do filter design with it. You'd probably have to put some kind of a linear amplifier on the output, but I mean, it's perfectly capable of doing that. Yes?
Looking at your diagrams and whatnot, I'm thinking of an application in digital mode. Have you had any experience like PSK 31 or anything like that, going into one of the higher clock rate chips?
Yeah, as a matter of fact, that's why I'm looking at the 809959. Because I can do phase shift, frequency shift, and amplitude shift keying.
Any experience with harmonics on digital modes, true digital modes?
As long as you're down below about 33% of the rated clock frequency for the device, they work fabulous. Now, building a filter for it, it's pretty simple, and then run it into a linear amplifier. Yeah. Anything else? How did I do time-wise? All right?
No.
Never are.
No. Thanks so
Okay.
much, Doug. Appreciate it.